And we just talked about how to write down equations of normal lines. You see, and for normal lines, what you need to do is you need to keep track of the coefficients in front of x, y, and z, right? So what are these coefficients? Let me actually do it right here. So you see, in this, this is a nice way to write it, but if I want to write it in the way we usually write, I have to put all variables on the same side. So instead of writing like this, I would have to write f sub x, x minus x0, plus f sub y, y minus y0. And then I would have to take the other guy to the side also. So that means the coefficient here is -1. So what is a normal vector then? That's this green vector that we talked about earlier. It's just f sub x, x0, y0, f sub y, x0, y0, and -1. So that's a normal vector. And now you can write down the equation of a normal line by using this as a direction vector for that normal line, right? What do we need to write down the equation of a line? We need to know the starting point, and we need to know the direction vector. Well, the starting point is given. It's x0, y0, and z0, where z0 is, again, just the value of the function at x0, y0. And then the direction vector is just this numbers, fx of x0, y0, fy of x0, y0, and -1. And then you have to choose a coordinate along this normal line. And so let's again use s as before as a second. But in this case, you could use t because we haven't used t in the setup yet. So, okay. So this is the equation of the normal line, or parametric representation more precisely of the normal line. So that's most of it. That's like 90% of the material we've done. And then there are what we also did last week. Last week we started to discuss various aspects of just general aspects of differential calculus. And the first topic we discussed here was limits. Right? So I kind of have to. It doesn't quite fit in either surfaces or lines. So I have to start. I would have to start a different topic. That would be 3. Right? And so that would be elements of the differential calculus. This is something which we will continue to work on for the next couple of weeks. And here we have limits. We talk about limits, different aspects of limits, and continuity. And then we also talk about partial derivatives. And finally, we talk about the differential. Although the notion of differential is, of course, as I explained in great detail last time, is very closely related to the notion of tangent plane. Tangent plane is a graph of the differential. So if you understand tangent planes, you understand the differentials as well. Okay? So that's roughly the summary. That's some summary of the material we've done so far. And now we have a few minutes left, so you can ask me questions. Any questions? Will there be epsilon delta proofs on the exam? The answer is no. There will be no epsilon delta proofs. But you have to know, as you can see on a mock midterm, there's a question about showing that the limit does not exist. Right? So you should be able to give an argument why it does not exist. Yes? What about proving that the limit does exist? That would be only in the case when it can be reduced to a one-dimensional case, and where you could use one of the results from one-dimensional calculus. Okay? On the mock midterm. Number 4. Okay. So it will take me some time. So maybe I will let me see if somebody has a shorter question, and I will get back to this. Is that okay? All right. So you were asking.
I don't know if I can short. Could you give an example of showing proving that limit does exist, like showing reducing it down to?
Oh well, there's one problem. So the question is, what kind of problems for existence of a limit should we know? A good example is a problem on homework in that section where the limit can be written in polar coordinates. So the function could be written in terms of x squared plus y squared, and then it becomes something like r squared times logarithm of r. So that's exactly the kind of example I have in mind. Nothing else. No, not squeeze theorem. Okay. Go ahead. Will there be true and false questions? Possibly. S represents a parameter of S is a parameter. It could be, you could use letter T, for example. Okay. Hyperbolic. Oh, hyperbolic trigonometric functions. You mean? No, you don't need specifically to know them. It's okay. Yes. I'm sorry. Polar drawings. The question is whether you would have to sketch polar drawings. Polar drawings are fair game because we studied them in class, right? And there have been lots of them in homework. Of course, I will not ask you to do something incredibly complicated, but something very basic like r equals cosine theta, r equals cosine 2 theta, r equals 1 plus cosine theta is something that you definitely should be able to do, right? Okay. Say again. Yes. I don't understand. Yeah, it's actually, guys. I don't know. Maybe it's not a good idea. Maybe you would rather me talking. Because I thought that you might be interested in some of the questions your colleagues have, because some of them might open something for you as well. So, but we cannot do it if people talk to each other. All right. Right. Oh, you mean for limits? Right. So for the limits, I already explained that you could have the homework. You have this function x squared plus y squared times something like this. Maybe not exactly, but something very similar. Is that what you're asking? So in this case, you should be able to explain why there is a limit when x and y go to 0. And the way you argue is by saying that in terms of polar coordinates, this is r squared times logarithm of r squared. And so the limit when x, y go to 0, 0 means that r goes to 0. So effectively, answering this question is simply equivalent to answering the same question, but for this function in one variable. And therefore, you can use the methods of one variable calculus. And the method of one variable calculus here is the L'Hopital's rule, right? So you can easily do it by L'Hopital's rule. This is something you need to know. In principle, since this kind of problem was on homework, it is fair game. Okay. Yes. Next. What exactly is perimeter? Parameter. What exactly is a parameter? In parametric curves? Right. So the question is, what exactly is a parameter in a parametric curves? Well, so to answer this, we look at the general curve, say in R3 in space. Okay. And what does it mean to parameterize it? Well, for me, the easiest way to think about it is as follows. So think of this curve as a rope, which is somehow hanging in the air. Okay. Like here's a curve, right? But it could be complicated like this. But if it is a rope, you can always just stretch it out and make it into a line, right? You can always just straighten it out, straighten it out. That's what I mean. Just straighten it out and make it a straight line. When you make it into a straight line, you can introduce measurement on it. You can just pick a point and say this point 0, and after that you'll have 1 inch, 2 inches, and so on. So you can put a measurement on it. But if you could do that to this curve when you straighten it out, it means that so you can just mark each point. Each point will have a certain distance from a given point 0. So that's the parameter t. Then you put it back where it were. But now each point has a parameter. So that's what I mean by parameter. You see what I mean? This is like parameterizing. We are not surprised by the fact that we have measuring instruments that they are parameterized. In other words, when we measure things, each point on this little ruler, has a marker, right? But that's because usually we mark things on straight lines. So here we deal with something which is not straight. What I'm trying to explain is that there isn't so much of a difference between the two, because even if you have a complicated curve, you can always straighten it out, and then you can view it. You can apply the same procedure to it as to a straight line, and so then you can mark each point by a certain number, right? And that's the x coordinate. All right? Anything else? Okay. That's a kind of metaphysical question, philosophical question. Are the problems going to be harder than the homework? On average, I think they will be about the same as homework. I mean, at least I aim them to be about the same level as homework, on average. But it's something in the eye of the beholder. It will be harder than what is. They're not going to be much harder in any case. Same kind of problems. I think that the reason why I posted the mock midterm is precisely to give you an idea what kind of problems I would consider putting on the exam. Right? So I think that gives you an idea. And speaking of which, let me go back to the question about number 4. Number 4. I haven't forgotten. Number 4 on the mock midterm. I'm very proud of this question because it combines so many different things. It's too bad I cannot use it now in the midterm. But maybe something similar. I'm certainly not putting this problem in the midterm now after I explain it. But okay, so let's calm down. So do you want to hear the solution or not? Yes. Okay, but then let's calm down a little bit. Okay? All right. So we have to first sketch this surface. So see, I'm going to do it now in real time because of course I don't remember. I don't remember what the surfaces look like, and I'm going to just try to guess. So first of all, I see that there is 1 plus and 2 minuses, right? Right? And so, but I don't remember which one is it. Is it the one with 2 parts or with 1 part? So how do I tell? The way I would tell, of course, you will have one way to do it is to write all of this on your cheat sheet. But then you will be using very valuable space for this. Whereas in fact you can very easily deduce this by just looking at it. And what I see is if you take the y squared and z squared to the right hand side. So it's 1 plus y squared 4 plus z squared 4, right? So what you see is that this is greater than or equal to 1. Right? It's greater than or equal to 1. So that means that if x is between -1 and 1, there is no chance that I can solve this. Right? So that means there's a gap. There's a break. The x equals 0 plane separates two pieces of this graph. And now I see that it's a hyperboloid with 2 parts, right? So, and the x equals 0 plane is the yz plane. It's the yz plane. So that means this is 1 like this, which will be exactly the point 1, and the second one, which is at -1, will be like this. Like this, right? So that's the way I would draw this picture. Now, well, there is this 1/4, but just to sketch it, it doesn't really matter, right? So that's the first thing you need to do. Second, we want to compute the surface area of the part of the surface bounded by the planes x equals 1 and x equals square root of 5/2. So here's x equals 1, and x equals square root of 5/2 is something which is just above 1. And why did I choose square root of 5/2? Because then, if I look at the plane x equals square root of 5/2, I will get, and I intersect that plane and this hyperboloid, I will get a circle, right? And what is that circle? So it will be square root of 5/2 squared equals 1 plus y squared over 4. Well, let me just write it here. So this will be like 5/4 equals this, which means y squared over 4 plus z squared over 4 equals 1/4. So that means y squared plus z squared equals 1. Okay? So that's the circle. And now to compute the area, I want to represent this as a surface of revolution. Right? So now a revolution of what? It will be a revolution of this curve in the xz plane. Right? So I just have to draw this curve. Of course, you have to remember that I have to look at it not from this perspective, but from the back of the blackboard, so that x goes from left to right. If I look like this, x goes from right to left, but I want it to go from left to right. So actually, it's going to start at 1, and it's going to go like this. Right? So in fact, what I want to do is I want to say, if you want, it could be maybe it's better to do an xy plane. Let's do it in xy plane. So to do it in xy plane, I have to put z equals 0 in this formula. So I put z equals 0, okay? And so what I get is x squared minus y squared over 4 equals 1. Right? So that's actually hyperbola. That's a hyperbola. It's part of the hyperbola. So what I'm saying is that I want to go from 1 to square root of 5 over 2, and then the formula for the formula for the surface area is going to be 2 pi y, right? 2 pi y times square root of dx dt squared plus dy dt squared. So this will be from, well, I have to take from alpha to beta, where I would have to write some parameterization for it. I would have to write some parameterization for this curve, and as x is some f of t, and y is some g of t, right? And so t will be from some alpha to beta, and right, and then I'll have to take this integral. Does everyone agree with this? Okay. So now the only thing I think, I'm afraid that I'm out of time. So I'm saved by the bell. But so I feel as though I should let the people go, but I will be happy to continue and explain the rest after a 5-minute break during the office hours. Okay. So let's stop here, and good luck on Thursday. So I'll see you on Thursday at 3:30. Exam starts at 3:40, and now we have office hours.